Okay, let's pick up where we left off. There isn't going to be any Kahoot today, so you can happy or sad about that as you are wish to do, want to do. Okay. So this is our view of out of order execution. I will talk about the exam a little bit later, but not right now. I want to make sure we wrap this up, get through all of the necessary parts for your first assignment. We can talk about the exam at the end. This is the view of all of the moving parts, some of which we've talked about for how they relate to this and some of which we have not. But let's just again look at this whole overview and make sure we get the right sense about it. So all of the parts in gray, whether they are participating in this out of order section or not, have an ordering component, right? So my reorder buffer, it's kind of in the name, right, is an ordered component. It's a FIFO queue. Right? Fetch, decode, rename, and dispatch are in order. Commit is in order. I will scream this repeatedly that commit is in order. We get to commit later. I will put it in bold on the second exam. Repeat after me. Commit is in order. Good way to get a 0. Okay. Load store queue has some ordering, right? There will be things that are happening dynamically in not program order, but there are other things that have to be maintained in order here. I need to know if a store is older than me or not, in a way that I do not need to know if an add is older than me or not, right? There are ordering properties that need to be maintained in the LSQ because we have not eliminated war and WA here, right? We've just done that for registers. Okay. To do our renaming, we had the map table, which is a new structure here, right? We have our free list, which is going to help us also with our renaming. Ready table is associated with the status of the physical register file, but is used by dispatch, right? Some of these things have just always been here. We just haven't talked about them. There is still a DTLB and a Dcache. There is still an ITLB and an iCache. And we'll talk a little bit more about the BHT and the BTB and so forth on the next few slides, or at least mostly the role of branch prediction. And finally, the architecture register file, to the degree it exists as a separate entity, logically is being written here at commit. Right? We do not update the values of any of our actual instructions until we know they actually happened, and they happened without any exceptions, and then and only then we modify the externally visible state of the machine. Okay, so with that in mind, let's keep going. Again, all instructions commit in order. All in order. Everything's in order at commit. Okay, so this is when you become the oldest instruction in the machine. Nothing in front of you could possibly have caused an exception. No branch in front of you could have meant that you were on the wrong path the entire time. You definitely happened. Nothing went wrong. Great, right? We are contract compliant with our original one instruction at a time, view of the world, and you can actually modify what the external world can see, right? And now that we are done with you, we can also free up some of these resources. Right, so we're going to write the contents that we computed. If you have an output in the register file, we're going to free the overwritten physical register because nothing else could be depending on the value that you had computed at this time. You are the oldest instruction, and you overwrote some other previous value, so nothing else could be using it. It would have been in front of you. For stores, right, at commit, right, things are now eligible to be pushed to the data cache. Again, they're in the store buffer, so could it happen after this cycle? Yes. Right. So a simple optimization in the store buffer is, if it's a hit in the cache, I write it right now. If it's a miss, I'll write it, eventually. Right? I can play around with policy there. Buffers let you delay things. That's what buffers are for. Okay. But at this point, right, we would mark it as done. Even if it's in the store buffer, we would have a bit that would mark that if we were being lazy in draining the store buffer. And we'd free the LSQ ROB entries. Now, we don't need to free the IQ entry because Why don't we need to free the IQ entry? So that got freed a long time ago. That got freed as soon as this instruction issued. If the instruction is completed, it must have already issued, right? So whenever it actually went out to go execute, it left the IQ. Things do not stay in the IQ, right? Things stay in the ROB the entire time from in order back to in order. Things are only in the IQ until they actually go and execute. So that's already been freed. Don't need to forget. Okay, so what else is the ROB for? Right, so I have alluded to it by the reasons that we have waited until you were at the head of the ROB to be committed. If there is a branch misprediction or any other sort of misprediction, right, you can delay until this point. You might try to do something earlier. You can be more aggressive, but it's certainly sufficient to wait until this point to handle any misprediction. And you definitely, absolutely need to wait until this point to deal with precise exceptions and interrupts. Okay. Excuse me. Again, the standard poster child for this is if I have a null pointer that I'm loading that's causing a page fault, but it's on a path that I never would have taken because the branch went the other way, right? No one should ever see that this happened. Right? No one should ever see this wrong path code talking to the outside world. Precise interrupts are very important. Your software stack relies on them. Your operating system relies on them. All of the contracts between software and hardware rely on this working, right? If you don't support that, not going to work. Okay, so what are you going to do if it turns out that the oldest instruction is telling you that there's something you didn't handle, potentially for hundreds of cycles? You're going to flush all the state behind it. All right, I get to the very end, I'm like, oh, this branch was mispredicted, which means that all of the instructions after it are garbage. Whoops. Right? Could I have figured this out earlier and done something? Yes. Are we going to talk about that? No. We're not going to talk about aggressively, mid pipeline doing partial flip. No, we're going to talk about the sledgehammer approach to this. This is correct. This is simple. This will get you the right answer, right? You can try to optimize it more later. Okay, so we're just going to flush everything, which means that, in fact, we also need to unwind the state of our machine to the state that it was in back when this branch entered the out of order execution window, right? Because up until rename, right? That path actually we're not so worried about. I mean, yes, you have to flush the instructions after it, but it doesn't really do much. It's just occupying some queue space, right? What we need to restore is the state of the ROB, the state of the IQ, the state of the LSQ, the state of the map table, the state of the ready table. But we can do this because we have enough information carried along with this instruction to undo everything that we have done. Right, so how do I update the map table? And back to what it was before. It's like, well, I know what register I'm writing, so that must have been on the free list. I know what register I overwrote, so that must have been the old value that was in the map table for the architectural register that I am updating. And I can do this in reverse from this instruction, walk backwards all the way through. Now, in a real modern 2022 machine, are you going to, in general, instruction by instruction, unwind every single thing? Sometimes, but not usually. Right? What they will do in practice is they will mark branches as high confidence or low confidence branches. If it is a high confidence branch, they're pretty certain they're going to be right. Then, if they did get that one wrong, you would actually do this. It would be very slow, laborious, and you do it. If it is a low confidence branch, they will take a checkpoint of all this state, and because they aren't actually very confident that the branch is going to be predicted correctly, and they think this is more likely to happen. And in that event that it is in fact mispredicted, they will flush everything, restore the checkpoint. Right? So hybrid mechanisms, lots of fun complexity. The net effect, however, is the same, and the impact on the wasted work is also the same. Right? So we'll see some slides that that show you just how much these end up throwing away, even with fairly accurate branch predictors. Right? Branch prediction, we've been working on it for decades. We're very good at it. We're not good enough. Okay. Okay. So we got to update everything else. Similarly, we're only actually going to know for absolute certain what way a branch went and update all of our branch prediction state in a non-speculative fashion at commit, again, because the branch might be behind a branch, might be behind a branch, might be behind a branch. So I might not have ever actually taken this branch. So the time I actually do take this branch, right, I want to actually update with the actual state that I had. Now, what this also means is that your BHT and your BTB are going to have to support, and we're not going to go into this, this level of detail, but I'm going to tell you, they're going to have to support understanding whether the history and targets that they are learning are known to be real or are speculative at the time. Because I can't wait to learn branch behavior for hundreds and hundreds of cycles across my 3-instruction loop. Right? So I'm going to be speculating on the things that I'm learning, but I'm not going to actually, in some sense, validate these speculations that I'm having even here in my training until commit. Again, commit is the only time that I know what really actually happened. Right? Okay. Interrupts, in the same way that we dealt with interrupts in our nice little 5-stage in-order pipeline, where we just sort of waited till fairly late in the pipeline, then said, nah, didn't happen. Treat it like a branch misprediction. We can do the same thing here, right? And for this, again, this is actually perfectly fine to take a long, slow, step-by-step unroll, because I have no idea that an exception is actually going to happen, right? I have no reason to believe at the time that I decoded some divide instruction, it was going to be a divide by 0, right? The odds are good it's not going to be, it's going to be fine. So a very rare event of things actually going wrong, yeah, I can go and enroll that. Even the more common valid exceptions, like page faults, are rare with respect to the number of instructions. So the page faults per number of instruction is a very small number. So the fact that it's going to take a little while to flush and restore that, fine. I mean, handling the page fault itself, moving something out of secondary storage, all right, that takes so long in comparison to this unwind. It's not really the bottleneck. Okay. Any questions so far on how we're going to recover using the ROB? We haven't talked about what all the data is, but assume that the ROB remembers a lot of stuff, right? So particularly, here's a list of all the things that it has to remember. Okay. So I need to know what the renamed destination register was. I need to know what the architectural register was that I'm going to be updating at commit, if any, right? I need the overwritten register. I need the original instruction address and its type. This is going to allow me to do some update my branch structures at the end. I need to record whether or not the instruction is actually done, right? Certainly an instruction can reach the head of the ROB and not have actually completed yet, right? I am a load. I have missed to memory. I will sit here at the head of your ROB, right? Like a student waiting for office hours for 311 for hours and hours, no, for hundreds and hundreds of cycles. And I need to know whether or not anything went wrong, right? So branch outcome, exceptions. If I have any other fancy things I'm speculating on, I would have more bits here for all the things that could go wrong. Okay. So again, I can populate all of this and initialize it reasonably at dispatch, right? So nothing changed there. In dispatch, I push things into the tail. If it's full, I stall. Otherwise, great. On commit, I remove it from the head. If the instruction at the head is not completed, I do not commit this cycle. Commit is in order. Thank you. Make it your mantra. If there are multiple instructions consecutively that are done and on the correct path, and nothing went wrong, and we have an n-wide commit, I can commit multiple instructions per cycle, right? So again, ideally, right, there's going to be some balance in the width of these queues, right? So I want my steady state of committing to be proportional to the width that I can do instructions elsewhere in this pipeline. So we have a multi-wide fetch, we have a multi-wide execute, we're going to need a multi-wide commit, or else, what was the point? Okay, and you can go play around with simulators just for OBs if you want to. Okay, so we are very familiar with speculating on branches, right? And we'll talk about how reliant, and that will sort of lead into the details of the first writing assignment when I would post that. It's probably going to be tomorrow. How reliant out of order is on branch prediction. So this we're well aware of. I have mentioned, but have not gone into much detail yet on load speculation, right? So if I am putting in a series of load and store instructions into the system, we don't know what the addresses are yet. And so now we have options as to how aggressive we want to be in actually sending that load off to the memory. So we can speculate that the action I am about to take will in fact retrieve the most recent version of this memory address. Okay. So as with branches, I am going to need to have a way to figure out if I was wrong, right? You can't speculate and then just say good enough, right? That only works in machine learning. Okay. And you need to actually then, if you figure out you were wrong, recover, right? Again, if you're going to add additional speculation mechanisms, then you're going to have some way to, again, gate the visibility of your speculation from becoming externally visible. Okay. Now, you're going to want to either ignore or buffer, depending on the nature of it, exceptions generated by speculative instructions. Now, why on earth would you ignore completely rather than just buffer? It's not something we talked about, but does anyone have any idea why you might want to legally ignore? In fact, even have the semantics of an instruction be that exceptions should be ignored. It's actually going to relate to speculative loads specifically. Guesses? Okay. So there is support in many ISAs for software prefetch, right? Even in, and then there are ways to sort of finagle even in the MIPS ISA. Imagine I was loading into register 0. What does it actually do? Well, nothing. I can't write register 0. So what if I just speculatively load to some address in register 0? The only thing I'd be changing would be my cache state, right? So there are ways to manipulate microarchitectural state speculatively. Since it's microarchitectural state, I don't need to recover it, right? I can mark certain instructions as exception ignoring, right? So I just issue them. If something goes wrong, I don't care. It didn't actually change any architectural state. It's merely there for performance reasons to make certain microarchitectural events more probable, right? So even if I would normally get a seg fault on whatever random address I did, I just ignore it and don't do anything. It'll be fine. It was a prefetch, right? So there are actually explicit prefetch instructions that have these exception ignoring semantics in a number of ISAs, or there are things that basically sort of reverse engineer this onto existing instructions to make things that are logically no ops, right? Do some work for you. Anyway, but in the general case, we will buffer the exceptions. Right? In general case, instructions can cause exceptions. We'll buffer them and deal with them at the end. Okay. So here is a depiction of a reasonable set of things that one might remember about instructions in the ROB. Right? Here is what Rob knows. Again, Rob has no IQ, but he does know a few things. Right? Remember, Rob has no commitment issues. That's why he went to the Red Wedding. Game of Thrones 10 years ago. The jokes are old. I will still tell them. Fine. Okay, so in our ROB, we need to know what instruction were you? What was the physical register you're writing into? What was the architectural register that was in point of fact supposed to be updating? What was the register that you overwrote? Are you in fact done? Were you a store that needs to actually have its data promoted into the cache at some point? Are you a branch? They need to check whether or not you were correctly executed and predicted, right? So with this data, I can do these tasks, right? So I will update T0 with the contents of P4, right? Now, maybe I just have a field that is the contents of P4. That would be fine too. I don't have to get them from somewhere else, right? Again, depends on how you're actually building the physical and architectural register files, whether or not you want to sort of carry more data with you or whether you want to sort of initiate a move at this point. They are logically equivalent, right? At the end of commit, T0 architecture will have the contents in P4. Okay. This was the renamed register. Clearly, there is no older instruction that is still dependent on the contents of P3, so P3 can go back on the free list. Right. So in the following cycle, P3 will be available. P3 is not available during commit. Right. I do not have a long set of wires and muxes that go all the way back from commit to rename. That'll happen later. Right. Okay. And we're ready. Right. So if this is the case of the set of instructions that are ready, right, then no matter how wide this machine is, if it's 1 wide, I will commit this instruction. If it's 2 wides, I will commit this instruction because this isn't ready. 8 wide, doesn't matter. I'm still blocked here. It is in order. Doesn't matter if these other 2 are ready. I can't do anything about it. Okay. When the time comes for this to actually be committed, right, I will make sure that this is presented to the cache, right, or at least logically marked as good to go from the speculative store buffer into the commitment store buffer. Right, again, you can delay it with an extra bit somewhere. In the branch, we will have to actually check, right, were you predicted correctly, which will tell us whether anything after that branch is in fact valid or a pile of steaming garbage. Okay, so in lower commits, we'll put P3 back on. And P4 will go on when the I do commits. Right. If this BNE, again, this is these are multiple copies of the same instructions. I'll remind you, these are not these static instructions, they're a dynamic trace thereof. If that first BNE that we encounter here is mispredicted, right? If we weren't actually branching back to this loop body, right? Then we would go through and unwind, right? We would restore everything to the state that things were in when this add-I had just been sent to through rename. Actually, we don't even need to rename the branch itself, but it's sent to dispatch, right? So we restore everything to the state that things were in before we dispatched this branch, right? Flush everything behind it and continue. Okay, so that would look something like this. If here was our old BNE that was mispredicted, and this is the state of our map table and our free list, right? I leave it as an exercise to the reader to do these step-by-step unroll. But if you walk back through this, right, I will claim there is sufficient information, right, to do that unrolling. We'll show you some examples of that on Friday. Okay. And then we'll restart dispatch here. Right, so we kick it all the way back to the front end of the machine. All the out of order is gone. And we restart dispatch for the BNE. And what's going to be behind the BNE at this point? Well, depending on how long it took to do that unwinding, I can have actually begun refetching things from the front end of my machine. However, I cannot actually push them through rename until I have restored the map table, but I could do fetch and decode if I wanted to. Those are independent of the things that I am restoring, if it takes multiple cycles to do so. Okay. So the other instructions might start to be filtering back in from the front end, from where those branches actually supposed to have gone. You can overlap those 2 events, right? So you won't necessarily feel the entirety of the branch restoration, because you're also filling the front bin back in while you're doing that. Okay. So load store queue. I'll post some additional auxiliary slides that go into a little more depth on the construction of the load store queue than we cover here. What we'll cover here is going to be sufficient to understand the scheduling that is occurring in the load store queue, but not really necessarily the implementation. So I'll post some additional slides for those who are interested on how you would actually build all the pieces together to integrate the store buffer into the LSQ and so forth. But for the time being, CAMs, lots of CAMs. Okay. So the load store queue is treated differently because, again, we do not know the addresses of all of our loads and stores, so we cannot use renaming to make a lot of our problems go away. So we're going to have to constantly be looking out for the dependencies and then react accordingly as they dynamically are discovered. Okay. So we are going to populate the load store queue with some ordering in mind, right? So we actually understand which of these instructions are older or newer, right? So in that sense, it is a very different structure than the IQ, right? And it is going to be handled differently in terms of what needs to be done for our loads and for our stores, right? So our stores, you think about what a store needs. A store is going to be worried about the order in which things are written into memory, right? So with stores, what I worry about is write after write. If there is a store that is older than me, and it goes to the same address that I am going to, then I need to make sure that these writes appear in the order that they are supposed to have occurred in the original program. Even if, in fact, there are no uses between these two stores, when we get to multiprocessors, it will turn out to be very important that these stores are presented to the rest of the memory system and the protocols that it may engage in with other processors in the order that they actually appeared in the original program. At the very least, you know, it has to be logically consistent within the single thread of execution here. Okay, so stores worry about other stores, and they have interactions with loads if there is speculation. If there's no speculation, they have less interaction. Loads are just worried about stores, right? So if I have a load and I have another load, it's fine. It's like read after read. You know, we don't care, right? Loads are read operations. They don't really modify. They modify register state. They don't modify memory state. So if there's a load and it collides with another load, maybe there's some clever things I could have done to not occupy a memory port. I can get the same value if it happened to be asking for the same thing, right? But that's an efficiency optimization. It's not a correctness one. If there's a load in a store, clearly I have to get the value that is the most updated value of that memory location. Okay. So while we depict this here as the source register issues here, we're again fudging a little bit. Probably would actually have split off the effective address calculation separately, and these would all be waiting on the calculated address. But same idea. We can think about the resolution of whatever the value here is something that are depending on. We're going to actually have to check the value of the actual computed effective address and see if that is what is matching for some of our ordering properties. Okay, so we're looking at two things. Has the address been computed yet? Right, that's a data dependence question with respect to the IQ, right? Or even if you sort of smushed it all together and had a very funny unified queue, like an RUU style from 1987. Same idea, right? So that's the same dependence order that we would have just for data flow scheduling. Until I know what this value is, I can't do anything. But I'm also going to be dependent on understanding the relationship between the value I computed here and the value that is computed by all things older than me. Okay, so out of the way, this one has the simple case of being the oldest. right? So nothing was in front of it. It could definitely have issued. Great. So if that load has gone out, right? And then you can basically say, okay, I can look at the readiness for my my destination, the readiness for my source. And even if this is good to go, right? Now we have multiple possible cases we could be in. So let's say that I know what the value of 0 plus P7 is, because P7 is not being written, but anyway, P7 was already ready already, right? So I can just go and at least perform the load. I have enough information to do this load. I don't have enough information to know if the value I get will be the most recent or not, because this isn't ready yet. So until I know what whether, actually in this case 0 plus P1 actually is ready. Fine. So until this address is computed and I check these two together, I don't know if they match or not. A lot of belaboring. Okay. Boop. Okay. So if P7 has just been computed, again, CAM address, same sort of stuff going on there. I'll mark all those things as ready. But okay. And similarly for the sources for the so let me actually take a step back here. So the history of the load store queue is actually the history of multiple separate queues that got merged together. So the stores have their own meaning an address and a value. Loads just need a value. The stores have their own store buffer that they're putting things into. As soon as they get the value, they don't actually need to put it in memory just yet. They just put it in the store buffer. So I'm hand waving over a lot of stuff here. So if it seems that I'm gesticulating a bit, it's because this is actually a much more complicated structure. And I really am just going to focus on what you need to know to understand the scheduling results that come out of it. Don't think it actually looks like this table. There's some more things that are going on, but enough information is there to get the right ideas out of it. Again, we'll go through concrete examples. That'll be clear. All right, so again, if we look back, we're still scheduling the same set of instructions. So store word P5 on P1, right? Load word P4 on P1, or next load word P8 on P7. Okay, so that's where these are coming from, and on the same screen. Okay, so this has already been sent out. It was the oldest. That's certainly fine as long as P1 was valid. Here, if we were able to compute this, then depending on the width of the machine, right, we should also have this. The readiness is there, whether or not it was already a computer or not, who knows, right? At some point, the value for P7 will be made valid. Good to go. We can perform that computation. Ready? At some point, the value for P5 will have been made valid. That's ready. Great. Okay. So in this state, right, if I've computed this address and it happens to be the same as this address, then I have the value I need. I can just forward it. I can forward between my loads and stores, right? If it's already in the store buffer, I'll read it from the store buffer first, right? If they are not the same address, right, then they're independent. I can just issue them both. Life is good. If they are the same address, but this value has not been made ready yet, right, then I know that this load is dependent and doesn't have a result value. I should wait, right? So again, this sounds a lot like dependence checking, because it is, right? So the same sort of way we're doing all the dependence checking for, well, is that value further down the pipeline? Is it going to be available, right, that we're doing in our in order? Similar things are basically happening here, except now it's not just the registers, it's an actual computed address that I'm checking against all of these things further down the pipe, right? And again, it's not just going to be 3 or 4 stages. This is going to be n entries that might be older me in the system. So I'm not going to do this in terms of if this, then this, then this, then this, then this, then I'm going to do some associative searches for matches. So I'm going to basically be broadcasting this to everything older, right? And actually, I'm not going to broadcast everything older. What I'm going to do is actually going to broadcast it to everything and only care about the things that are older than me that return. Again, I'm hiding a lot of detail in this little table. But logically, these ordering properties should be fairly clear. Okay. So dependencies are going to exist in your memory, right? I am going to be reading and writing the same structures. If I don't, I have a very uninteresting program. Right? So stores, we've already said, are committed in order, in program order from the LSQ, i.e. specifically from the store buffer as part of the LSQ. They don't get to commit until the ROB, but they get to put their value in as soon as they have it. Fine. Now, as long as these stores commit in order, drain the store buffer in order, put things into the store buffer in order, then the write after writes and other challenges from store to store will be resolved. In general, we are not going to speculate on stores, right? So can anyone think about why we probably are interested in speculating on loads, but not interested in speculating on stores? Why are loads and stores fundamentally asymmetric? Ask yourself about your in-order pipeline. Do stores cause stalls? Well, not in account of being stores, right? They might be dependent on something and they can't go, but the stores don't cause a stall because I already have the value, right? The value is already there. I don't need to go get it. I already have it. Someone else could just get it by forwarding, right? So anyone who's dependent on a store having happened can always get the value from forwarding because I already have the value. Yes? You had a question? No. Oh, you're just stretching. Okay. Okay. Right. But loads will cause stalls all the time. Right. So we want to speculate on loads because loads clog up our pipeline potentially for hundreds of cycles. Stores, the only way a store is going to stall if our store buffer is full. Okay. So we're not going to speculate on stores. We're going to do them completely in order. We're going to make sure that all, in fact, older stores have resolved their addresses before we even attempt to update any of these structures. And while that is going to slow the rate at which we can issue these stores and have them clear our buffers, it's going to mean that these problems are handled very simply. Right? If I have a total serial order on my stores, right, then write after write and write after read for the stores is simple. Okay. Now, with respect to the loads in the stores, since we do want to be a little more aggressive, we're going to try to figure this out more directly. Now, some of these are kind of obvious. If I have this pair of instructions, this is definitely a read after write. Right? If I have this order here, I do have write after read. I do need to make sure I get the value from before I do the store. Right? And write after write, again, handled by doing things in order. The challenge is going to be, in practice, not 0S1, 0S1, but more 0S2, 0S1, RS2, and S1 the same. How do I know? I don't know. I got to figure out the value. Right? So memory is fine. Okay. So stores will leave the LSQ when they are in fact fully resolved and their entry has been written into the store buffer, right? They need to linger around a little longer within the LSQ than they do in the IQ. They actually have to leave in an orderly fashion, right? There's an ordering property in terms of when I can actually retire them from the LSQ. So the loads are going to need to access data in the out of order portion. So stores, again, don't actually bother to update the data memory until commit, right? That's externally visible state. but we will issue reads to the outside world in the middle of out of order execution. If we do not, well, we won't get much done, right? 20 to 30% of your instructions are loads. They need their values. I can't just sit there waiting, right, until I become the oldest instruction in the machine. I guarantee you, your ILP will be basically nothing, right? You need to actually go get the data. As I already said, I could do load forwarding. That's nice, but it's not really very important. Load to store forwarding, kind of important. From a logical perspective, I would like to resolve anything within a structure rather than going and bothering the fairly expensive access to the memory system anytime that I can. You're going to need to check for this anyway for correctness, so you might as well just get the data at the time. So the phrasing for what I've been talking about, right, is bypassing. Right, so we're asking, when can a load bypass older memory instructions? Again, load bypassing a load, no big deal. Read after read, who cares? Loads bypassing stores, 2 cases, right? So even in the most conservative policy, load bypassing will be allowed. Right? By which I mean, if I know what the addresses are, I know non-speculatively whether or not there is a dependence. Right? So if I know what the addresses of all the older loads stores in the system are, so that loss of generality, here is some store. Let's say I have computed the value of S1, I have computed the value of S2. If I know they are not the same, right, I don't have to do these in order. Right? So let's say that T0 is waiting on some other load that's going to take 4,000 years to come back. Right? The store's not ready to go. If I know S1, I know S2, I've computed the addition of 0 to both of these, and they're not the same. Even in the most conservative scheduling policy, this load will go. Right? Because there's no collision, there's no dependence. Right? If I can non-speculatively understand there's no dependence, I'm good to go. Right? These are the same if I know that these 2 values are not the same. Okay. Right? If I have resolved this value, and this is some other unknown value, it's a proxy here, right? We don't know. So in a conservative policy, until I have resolved both of these values, right? Doesn't matter whether the question marks were here or here, right? Until both of them are known and known to be not the same, not so good. Okay. And again, load after load, yeah, who cares? So how much does this buy us? Okay. So it's a non-trivial optimization, right? So matching from directly from older stores is modest. You can measure it, but load bypassing is big, right? So being able to issue loads not in order by all the stores, even conservatively, will get you double-digit performance improvements. And if you go even more aggressively, right, you can go even further. Okay. So stores are going to stick around until we know they've actually happened. They're going to occupy be there in the LSQ for quite some time. Now, one of the things that will happen if you support aggressive load bypassing, where you are going to have loads speculate past stores that who have unknown addresses, then it becomes the responsibility of the store to then invalidate loads that have already issued. Right, so it'll increase the complexity of your load store queue. There'll be additional associative searches. If you have a conservative scheduling policy, then it's all the responsibility of the loads. Right, so if the loads are checking conservatively to never issue unless they know for certain that there are no outstanding stores they might collide with, then the store's job is very simple. The store just does a store. If you are allowing a speculative early issue of that load, it is the store's job to go back and invalidate any younger matching load that had already issued. more complexity there for the store side. Okay. Okay. And what does this all mean in terms of now that we've sort of gotten all of the components finally wandered through? So the key thing that we want to think about of what out of order execution bought us was a larger set of potential instructions from which to extract ILP. Right, so everything that is in the issue queue, I can see if you're parallel to issue this cycle. Right, everything that is in the ROB, right, allows me to go looking for more potential parallelism in the various stages of my machine. So the larger my scheduling scope, the greater the odds I will find something independent to do. Right, this is not a terribly complex intuition. Obviously, there are costs. Right, the larger my scope is, the bigger my physical register file needs to be, because again, 2/3 of your instructions define something. Every instruction that defines something needs somewhere to put it. Right, this gets more expensive. It gets slower. It gets power hungry. Right, some of the hotter parts of your chip are your physical register file. Right, you can actually tell the difference in temperature if you look at the fine-grained thermograph of your design. The issue queue has lots of associative search. The more associative search you have, right, the more power hungry and size constrained some of these things are going to get. They do not scale the same way as RAMs. Right, so the number of things I could be searching across within a single cycle has some limitations on how big this could actually be. Right, load store queue. Again, the more you're supporting speculation, the more associative searches in both directions you're doing. Again, will constrain the number of uncommitted loads and stores. Right, and they actually also have to linger around for longer to maintain some of these ordering properties. Right, so the other thing that's going to actually hit you before any of the hardware pieces, though, is this branch prediction. So let's just do a really, really simple back of the envelope calculation. Okay. Let's assume I can find some chalk. Let's assume that I have 1 out of every 5 instructions as a branch. That is certainly a reasonable assumption for lots of types of programs. Again, if you're doing matrix multiplication, no, this number is larger, but not lots of instructions per branch. But let's assume that I have some branchy program. It's making lots of decisions, like maybe it's server code, right? It's jumping through a whole bunch of lines and a million lines of Apache code. So 1 every 5 instructions is a branch. And let's talk about my window size here. Let's assume this is pretty reasonable. Let's assume I'm on the order of 256 instructions in my ROB, right? And yes, technically the ROB versus fetch, but let's again squint a little bit as we're doing back of the envelope here. What are the odds if I'm, roughly 255 instructions deep, and 1 out of every 5 instructions is a branch, that I'm still on the right path, right? So I have some branch prediction accuracy. There's some accuracy. Okay. So what this is really saying is I'm, 1/5 of 255. It's 50-ish, give or take. Again, back of the envelope, a small envelope, right? So whatever my accuracy is, I am now 50 branches deep. Okay. So even if this was 0.95, raise that to the 50th. And you will note that this number is no longer particularly close to 1. Right? Now, are all the branches uniformly? No. I mean, again, if you're multiplying a matrix, this accuracy is much higher than 95 and is going to sort of stay that way. If you're doing, really weird branching integer code, it's actually even much worse than this. So this is an average. We're squinting a lot. We're waving our hands. This gives you the idea of why this is fundamentally challenging. Right? I want a bigger and bigger and bigger window size. And depending on the behavior of my program, my ability to predict it, I can't even find the right instructions to put into the window, let alone figure out which of them are in fact parallel. Right? It's kind of a prerequisite. I can't figure out what instructions are parallel if I can't figure out what instructions I'm supposed to execute in the first place. Right? One of these things is sort of a stronger constraint than the other. Right? So if I could get all these things in scope, then I'm constrained by how big I can build these structures to exploit them. Right? But I am actually going to be very sensitive to this. Right? So 1 every 100 instructions is, well, wrong at 95%. And I have hundreds of instructions, but the odds are I have mispredictions. So again, when we go back to where we started, like slide 2 or 3 in this deck, and I said, look, the reason we're searching for this, the reason we're building all this expensive, complex hardware, we're doing these fun, interesting things, is we know there's gold in them there hills, potentially, right? But these numbers here are for a perfect dynamic superscalar data path that has an infinite number of rename registers, right? An infinite sized IQ, LSQ, and ROB. No limit on the number of instructions to begin execution simultaneously. Right, so effectively an infinite number of functional units. Perfect branch prediction, perfect caches, loads that can be moved before stores as long as there were in fact no actual raw data hazards, so perfect load speculation, and a 1-cycle functional unit latency. Right? So if you relax some, if you make some of these constraints a little more real, right, you don't get that, right? You get numbers like this. So let's take a little look at what this is implying. Okay. So if we look at the number of instructions that I could be looking at one time, and I look at how much parallelism I might be able to extract, if this is my only constraint, so I keep everything else infinite, I'm just sweeping the size of my IQ. Right? There could be certainly some jokes about the performance of your machine when your IQ is 2000, but we all know that IQ tests are flawed mechanisms. Okay, but clearly for things that we could actually build, just sort of this range here, right? Dozens to low hundreds for the IQ. There's still quite a bit of parallelism out there, but it's not 160 anymore. Even these very, very parallel-friendly structures for instructions per cycle are still in the dozens. Now this, if we could hit this, we'd still be really happy, right? This is like, what, 35 instructions per cycle? That would be amazing, right? Even this down here, all right, this is not bad. This is like what, 10, 15? So if we limit it to a large but finite IQ, so this first sort of initial drop here, right, where we're not like searching in parts of the program we're going to get to, several seconds from now, then we can look at the impact of, of branch prediction. Oh, sorry, there's rename registers. Sorry. We're also assuming, we are assuming a finite branch prediction. Assume here finite branch prediction, finite IQ. So a finite ability to push things into this window with the odds of them actually being correct. Given that our peak was less than 64 anyway, when we went to 2K, so without loss of generality, we can assume a 64-way issue capability. It's fine. 8,000 entry tournament branch predictor, so reasonably aggressive, right? And for renaming, again, this is going to sort of give you some sizing feedback on how big you should bother making your ROB, right? So you get, again, a lot of bang for your buck here, right? And indeed, modern ROBs are in the 256 plus range. Right? This is from 2003. It's been 20 years. But this, again, ILP is a fundamental program property. So These things are only going to change as a function of the programs themselves, not the advances in hardware. Right? What's worth building can change, but the properties of the programs themselves are actually mostly fixed. So if we keep putting more and more restrictions on it, so if I have a processor with no branch prediction, right, or just basically predict a static, predict whatever, you can see the ILP drops to negligible. Right? If I can't figure out what instruction I'm supposed to execute, then yeah, it doesn't matter what I do further down the line. Right? If I have perfect versus tournament's pretty reasonable. Even this you can see is a big drop off. Right? This is a very reasonable branch predictor. It's going to have for most of these programs a high 90s or 90+% accuracy. And you can see that the gap between 90 something and perfect is potentially, right, like more than 3x. So what's the right way of thinking about this? Right, we looked with all the way back to VLIW with if the compiler could look at our program and understand certain things about our dependencies and fundamental actual program semantics, could it expose lots of lots of parallelism? Sure, but the compiler was going to be fundamentally constrained by only having static knowledge. Right, there are lots of things it could not do because they were not sound as optimizations. Right? I can't arbitrarily move a maybe dependence. Right? I'm stuck with those. Right? Whereas in dynamic scheduling, totally in the hardware, right? The hardware is going to be more complex. It's going to be more power hungry. It is going to be physically larger. Right? There are going to be some other fun scaling issues that we will run into. But the hardware can dynamically, for the particular trace of instructions it is observing, figure out some of this on its own. Right? Now, again, it can't figure out all of it. Right? It's going to effectively, with branch prediction, do dynamic loop unrolling. That's good. So I fetch a small number of instructions. I don't have to bloat my initial program binary. As I can execute them, make more parallelism available. But there are things that were lost. So, for instance, if at the compiler level I knew that this pointer to structure A and this pointer to structure B, structure A and B are never overlapping. Then even without looking at the addresses of these two axes, I should know that they cannot possibly collide. It is very difficult to express that to the hardware unless your ISA had some way of doing so. Right? The hardware is going to dynamically rediscover some things that we did actually already know. Right? So there is a little bit of disconnect. There are some things that are lost. Right? And if you're looking for ways to get some efficiency, ways that you can give hints, ways that you can sort of help the hardware not learn, forget, learn, forget, learn, forget are useful, but it can discover, at least for the things that it's looking at, what's going on within its finite scope. Now, we want to fetch as many instructions as possible into that scope. So we are going to use branch prediction to speculate past many, many, many branches. Again, this is why, well, I said you could be aggressive about doing branch recovery early. Complicated, because you're not talking about doing one branch recovery early in the middle. You're talking about like doing 20 branch recoveries somewhere in the middle. Right? There are some complications we haven't really dwelled on in how do I understand as I'm going through all these various branches what information I want to feed back from speculative state back to fetch in my in-order side. Suffice it to say that there is some sort of stream that is informing fetch about which way you're supposed to be going in any given cycle. Right? We do have speculative updates to our predictive structures. We're not gonna dwell on that. Okay. But again, as long as we buffered everything, as long as we didn't let anyone know what we were doing, right, we are free to play around and speculate wildly. And just flush it, mispredict. We'll see some slides about how bad that is in a second. Okay. Renaming gets rid of all of our register carried false dependencies. Right. This does a lot of lifting for us. Right. Renaming is a big win. Right. Renaming is full stop just worth it. Right. Gets us a lot more access to ILP. Inside the middle of our pipeline, we are basically operating on a data flow execution model. You execute as soon as your operands are available and there's a functional unit that can do the operation you require, right? So for an add, as long as you know the two things you're adding and there is an adder somewhere, you're good to go, right? Memory, because we don't know the address ahead of time, a little more challenging. Again, while you can try to be a little more fancy in practice, simple is easy to reason about correct, and correct is very important when mistakes are billions of dollars. So just wait if anything hinky happens and flush everything and try it again, right, from the end of the commit queue. Again, exceptions are rare. This is a very reasonable way to do business. Branch mispredictions are not rare enough. And so you are going to do more complicated things like combined hybrid checkpointing, unrolling, fun mechanisms. Okay. So know how to do register renaming, right? That will be on the exam. You will be renaming registers. We will walk you through examples of doing issue and select logic. We will be talking about how to understand the ordering in loads and stores. And remember, commit is in order. Too many damn years seeing very, very wrong answers. Maybe I need to change the font size, right? Maybe I need a John Hancock version of that on the exam, right? Rather than just in bold. Okay. Also, when commit registers are free. Okay, so these numbers are a little dated, but they give you some sense of trends, right? So don't worry about the specifics, worry about some of the relatives. So if we look at these sort of we're at least up until really about maybe 4 years ago, a pretty good prototype of what a lot of these designs look like internally. And they were much, much more power hungry than their earlier friends. Now, we're looking at two trends here simultaneously, so it's a little tricky to ponder. So the transistors between here and here got much more efficient, and I'm still consuming, 2 to 3 times as much power. This complexity has a cost. So all I really want you to take away from this is growing your aggressive out-of-order wide machine is not free. They get extra special toasty. Right? They're not just bigger, they're also toasty. And again, we went here from 4, now we're at about, so 8 to 10. Okay. I'm going to skip the TikTok slide because TikTok's mostly dead at Intel. But yes, there is a differentiation between architectural design advancement and technology advancement. But let's focus a little more here. Okay, so again, this is a 10-year-old machine, but it gives you the right sort of relative sizings of some of these structures. Okay. So 56 total in decoded instructions sitting around, an ROB of 192 microops. Again, Intel, not a RISC ISA, ugly ISA to try to do anything fancy with. So they cheat, they translate their ISA into internal microops and do very risky sort of things with those in the middle, and then fix it back in post. And they've been doing that since the Pentium Pro. Okay, so 192 microops. So those are not Intel instructions, but those are RISC-like instructions, mostly. Okay, relative to the IQ equivalent in the Intel machines of the day, 60. Right, so I can have 192 instructions in my window, but only 60 of them can be checked for readiness in any given cycle, because this structure is more expensive to scale than this one. Right. Renaming, size of the physical register file. Note that this relationship sort of makes sense. If I expect that about 2/3 of my instructions need to define a register, I don't need to make my register file quite as big as my ROB, right? But that are going to have to scale proportionately based on my ratio of branches, stores, et cetera, that don't define anything. Okay, floating point, separate. We haven't talked really about floating point, but we have an integer register file, floating point register file, do the same thing. Now, One of the reasons we haven't talked about floating point and reordering has to do with the fact that the math in floating point land is differently sensitive to reordering. So, lack of associativity is its own sort of thing. We'll not worry about that. But depending, well, we're not going to worry about it. Okay, right. Load buffers. We can have lots of loads, stores. This is sort of the size of our store buffer. This is, as you can see, is a little bit asymmetric. I'll post some addendum slides on how you actually build a modern LSQ. But note that these are roughly on the same scale as your IQ, give or take. Okay. So here's some pictures to give you a sense, again, to calibrate our very simplified model versus, again, these are your 10-year-old machines, but they still give you the right sense of how to look at a. You go look at the same sort of diagram from something coming out in 2020. It will be very similar. Right, have a few more moving parts, but this will at least allow you to go out and read that. Right. So front end branch prediction, big, complicated, actually full of trade secrets as opposed to just patents. Branch prediction is fun. You have your actual instruction cache because it's x86. So these are x86 instructions. I'm fetching these. Decode for x86 instructions is a thing. We're not going to talk about that too much. Other than the fact that even figuring out where the instructions end is its own pipeline stage. Then when I've actually figured out where the instructions actually were in that pile of bits that I just pulled out of memory, I put that in a queue. I have 4 different decoders for different classes of how nasty the x86 instruction actually is. Right? I can decode a simple like +1 with a simple decoder, but x86 does have things like call, which does all the stack setup as well as the, it's got complex stuff in there, and turn into some number of micro-ops. I can cache this if I've already in fact decoded this before and turned into micro-ops. So this here is basically more like what you're sort of thinking in terms of starting your fetch and decode, except that of course I have to be fetching here. So a little more complication on the front end in x86, but if you smush all this front end together here, you have a cache, you have a queue of decoded instructions. Great. Okay. So starting with that set of decoded instructions, right, you are then going to dispatch them, right? You're going to rename dispatch into the reorder buffer and into the IQ. This happens to do it sequentially. That's fine. Right, we're having a model where we do it in parallel, but again, they want to hit much higher clock frequencies than we do. Okay. So in this 60-entry unified reservation station, again, some of these get split up in later designs, but same idea. Right, you are having different ports. Those different ports are associated with sets of functional units. Right, so this is an 8-wide machine at peak, but not 8 of anything. Right, so in particular, this only does stores. So that's the only thing this port can do. These 2 only generate addresses. You want to do anything else, you're out of luck. Right, this port, you could schedule pretty much anything. Your floating point is being sent over to here. Right, this is specific for store addresses. Here's another place you can do branches. These diagrams will look more or less like this on any modern design. Right, some set of subsets of the things you can do associated with some number of ports. This is unified. You could carve this up, right, and say I have a separate scheduler just for my floating point, separate scheduler just for my branches and loads. That would be perfectly valid, right? Different ways to build the same sort of logical structures. They have different trade-offs, but in terms of what's going on, we're still reflecting the ordering schemas that we've done so far. One other thing, and we will come back to this next set of slides when we get back to caches in the memory system. One thing that aggressive out-of-order superscalar machines need is a means of getting all of their data into that core, right? So one of the things that you can start thinking about, even before we think about the memory system itself, so again, we can come back to the slide later, is what is the bandwidth that you would actually be hitting in your register file, right? What are the relative scales of bandwidth at different points in your machine? Right. So before we go to there, let's just do a back of the envelope exercise. Let's say I'm only doing 4 instructions per cycle times 2 operands per instruction times 8 bytes per instruction. Right, so this is 4 inst, 2 operands, 8 bytes per operand, right? So I need, multiply all these together, right? 64 bytes per cycle, right? Just to feed the operands, right? And if I'm doing this 64 bytes per cycle at 5 gigahertz, let's keep it in powers of 2. Let's do 4 gigahertz, right? Then what's the bandwidth I need in my register file? Well, 4 times 64, last we checked, 256 gigabytes per second, right? 4 is not very aggressive, right? You need basically terabyte per second scale bandwidth to feed these things. Note that your main memory does not provide you with terabytes per second of bandwidth, right? So your main memory is not going to feed this. You're going to have to be efficient. Now, again, these are older machines, but these were of the same day, and they're going to give you the right insight about some of these costs. So if you look here, here was that ARM A8 we saw in static scheduled in order. It's a nice, simple little two wide processor that at 1 gigahertz ran at 2 watts. Right, so not apples to oranges, but you know. So here was a comparable Intel design, many generations old, but same ideas. So for 60 something times the power, right, you were able to go 2.5 times faster in terms of the clock and have 4 times as many cores, right? If you multiply all these out together, however, you will see the efficiency win is still here. If I care about joules per instruction, right, I still want my in-order core. If I care about peak performance, there's no contest, right? This beats the snot out of this, right? But it does so by being aggressive, and that aggressivity has an efficiency cost. Bloop. Okay. Yeah. So if you want to look at where retirement goes, here's a sort of another diagram. You can see the same sort of entry. This is a slightly older design. You can see how they've scaled. Right. We're not going to dwell too much on it. We can come back later. Okay. But I give you that just to give you a sense on even a slightly smaller machine. You want to do a little more apples to apples comparisons. We're just about out of time. Okay. So let me stop here actually and just briefly talk about the exam. We'll pick up here on Tuesday. So note that regrades are open on Gradescope. So if there's anything that you want to do a regrade request for, go and push that into Gradescope. We'll do it through Gradescope. The mean currently is sitting at around 57 to 58%, a little under target. I was hoping for 2/3 or thereabout, a little higher. I imagine the mean will trickle up a little bit as regrade requests come in. So this is probably closer to around I expect 60, low 60s. Again, given the grading scale for this class, not too terribly bad. And the class is curved. So, but do go take a look at that. The rubric is reasonably detailed. So you should be able to figure out what you got docked for on all of those questions. And I expect I will be hearing from you via Gradescope for a variety of you. Okay, have a good weekend. See you next week.